and I'm going to expand this to full screen. I don't know if it makes any difference or not, but I'll do it. And I'm also going to then probably start with the whiteboard, because that's basically all we got in this course, right? Okay, now the next thing to do is try to get this mess out of the way. You can't see what I'm talking about, I don't think, but the toolbars are basically nothing but in the way. Okay, so move that toolbar, move this toolbar, okay, and then I'm going to move all of y'all just a little bit, myself as well, to get that. And then I'm going to move the whiteboard. I don't know if you can see what I'm doing or not, but I'm going to move the whiteboard to try to get the most possible access to space that I can. That's probably about as well as I can do. Okay. Now, were there any other questions, concerns? Aaliyah had questions on homework sec 2.3, which is basically the section we're in now, on problem number 1. Okay? And here is that. So this, by the way, is page 71. If you got books, and I think all of you said you did have some type of book, right? An ebook, let's say 71, and I wrote a 1. So that's going to be an ugly 7. Page 71, this is 2.3 exercise. And we're going to start with number 1. Whoa, that's ugly. All right. What they give us in number 1, it says, they give us 2 matrices, A and B, says show that B is the inverse of A. Okay? So here's matrix A. And this is 2, 1, 5. Oh, here comes Ricky. Ding, ding, ding. Perfect attendance again today. Way to go, team. Okay? That means perfect attendance this week. That means perfect attendance for 2 weeks. Okay? And before that, before Aaliyah was in the room, we had perfect attendance for 3 weeks. And before Jemanuel was in the class, we had perfect attendance the week before that. And only the first day of class were we missing 1 person. So, wow, this has been a great class for attendance. Glad. I appreciate it. Welcome. Really like the, at least feigned enthusiasm. Oh, well, I didn't say that, did I? Okay. So here's matrix A. By the way, Ricky, if you're in now, we're doing homework problem 1 on page 71, exercise 2.3. And here it is.
You sounded muffled. I couldn't hear you.
Okay. We're doing the homework exercise from section 2.3 on page 71, number 1. We're going to do a few of these until y'all say stop. We got it. Okay. So here is the first. A is the matrix 2, 1, 5, 3. That's a 2, 1. It's supposed to be a 5, 3. Okay. Here's matrix B. Okay, and matrix B is also a 2 by 2, which is good. And I think that's a 3, negative 1, negative 1, 2. 3, negative 1. I said negative, it's negative 5, 2. Now, One of the first, and this was just a very minor thing that happened on this problem, you're writing on line paper, which I like to do too, but it happened to be that -5 here, the minus sign showed up right on top of the line, and then when you went to the next step, you didn't notice it. So there was a first little problem, but that wasn't the major problem. What you're asked to do is show that B is the inverse of A. And your approach was perfect. What you do is look at, and you wrote it down properly, AB. Okay. Now, what AB is the product of A times B. Now, unfortunately, it looked like what you did was sort of start adding A and B, not multiply. So, again, here's my technique. It may not be the best one. It may not be one that makes any sense to you, but it makes sense to me. A is a 2 by 2 matrix. B is a 2 by 2 matrix. You can multiply them because the number of columns of this one, 2, is equal to the number of rows of this one, 2. So your answer is going to be the number of rows of this one, 2, by the number of columns of this one, 2. So the answer is going to be a 2 by 2. So what I do when I'm multiplying matrices, I put a blank for every one of the entries I know is coming. And since this is going to be a 2 by 2, I put 2 blanks in the first row and 2 blanks in the second row. All right. Now, next thing I do is identify the position of this one. This position here is first row, first column. This blank here, first row, first column. How do I get what value it is? I do the first row of A, multiplying it by the first column of B, adding as we go. So that would be a 2 times 3, which is 6, right? Plus 1 times -5, which is -5. 6 minus 5 is 1. Do you see how I got that? This is how we multiply matrices.
So you did 2 times 3 minus 5?
Okay, yeah. 2 times 3 is 6, plus 1 times a -5 is -5. So 6 minus 5 is 1. But you multiply, it's not just you subtract 5 from it, it's this row, first row, by the first column, multiplying the corresponding elements, adding their sums. So 2 times 3, 6, plus 1 times a -5, that's -5, 6 minus 5 is 1. Do you see that?
Yes, I do.
Okay. Now we go to the next one. This entry right here is the first row, second column. So we do the first row again of the A and multiply that as we go to the second column of B. So the first entry will be 2 times -1, which is -2, plus 1 times 2 is +2, -2 plus 2 is 0. Do you see that?
Yes.
Okay. Again, you multiply matrices, identify your position, what row, what column. This entry down here, second row, first column. So you say take the second row of A times the first column of B. Always do them in the order that they show up here. Second row of A, that's 5 times 3 is 15 plus 3 times a negative 5 is a minus 15. 15 minus 15 is 0. Okay? See that?
Yeah.
Okay? And then this entry is the second row, second column. So we take the second row of A, multiply it by the second column of B. So that's going to be 5 times a minus 1, minus 5, plus a 3 times 2, 6. Minus 5 plus 6 is 1. Do you see that? Now.
Yeah.
All right. Now, that's looking good so far. And the reason I say so far is we've multiplied the two. Now, if these are inverses of each other, that means that A times B should be the identity matrix of the appropriate size. And indeed it is. Okay? But to completely verify, we need to, and you did this too, figure out what B times A is. Now, you can do it backwards if you want to. I find it confusing. Okay? Now again, here's what I mean by that. I'm going to write matrix A over here again so I have it in the right order. Because my wife will tell you I'm really staid and rule bound. Okay? I do things the same way. I have a system and I try to do it the same way, otherwise I get all screwed up. So writing A again, that would be 2, 1, 5, 3. That's matrix A again. Okay? And again, I go through this liturgy every time. This is a 2 by 2. That's a 2 by 2 because the number of columns of this one, the second number, is the same as the number of rows of this one, the first number. Wipe out those. They're the same. And that leaves you a 2 here, number of rows here by 2 column here. So this is going to be a 2 by 2. Once I've established what size it is, then I put blanks in there. You don't have to do this. This is just my little simple-minded way of doing it. Okay? And then I ask myself, what is the address of this place? Well, that's the first row, first column. So in the order, I do the first row of B times the first column of A and add as I go. So this gives you a 3 times 2, 6, plus a negative 1 times 5, negative 5. 6 minus 5, again, is 1. Okay. Are you willing to do this one? Or you want me to do it?
I can try.
Okay. So what's the address of this place right here?
So it will be first row.
First row.
Okay, so it would be like 3 times 5.
Okay, now. Say it. Okay. First row, second column, right? That's the address right here. First row, second column, right? Okay, that place right there. So you do the first row of B times the second column of A. So you do 3 times 1.
1, okay.
Yeah.
It was just 3, and then you do 3 times 1 is 3, and then it will be minus 1
Times.
times 3.
Yeah, and that is?
Okay, sorry. is going to be, they'll just be 0 because it'll be 3.
Say that again. I couldn't hear.
They'll be 0 because
0. You're absolutely right. Yeah, because it's a +3 -3. Okay. Willing to do this one? Give me the address.
Okay, for we're still on the first row. No, we're on the second row.
Yeah.
Second row, second column. Okay.
No? Wait. Which column?
No, second row, first column.
Got it. Okay. So what would we do?
So it'll be -5 times 2.
Yeah, which is?
Which is -10.
-10.
And it'll be +2 times 5, right?
Which is?
Which is 10. So
Yeah.
it'll be 0.
That adds a 0 too. Ding, ding, ding. Okay. And what's the address down here?
Oh, for
This
okay,
one right
it
here.
will be 2 times 3.
Okay, now where are you getting this? This
Oh,
is,
no. It'll be 2 times 5.
okay, where are you getting that?
I don't know. It takes me a while. Sometimes I'm a little slow.
Okay. Well, first, give me the address of this place right here. Where are we, Waldo?
Okay, so second column, first row.
Okay, wait, no. You're in the second row,
Oh, yeah, okay.
second column, right?
Mhm.
Second row,
Oh, so it'll be
second
like,
column.
it'll be -5 times 1,
Yes, which is?
which is just -5,
Plus,
plus 2 times 3,
which is?
it'll all equal to a -1.
Not a negative,
I mean, a positive 1.
positive 1. -5 plus 6 is a +1. And sure enough, not just AB is the identity matrix, BA is also the identity matrix. Ding, 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 you've just shown that these are inverse matrices of each other. B is an inverse of A, but that also means A is an inverse of B. Okay? That was number 1. Okay? Now, do you need to do another one, or you think you got the rest of those okay? 3 through 5.
I think I'm pretty good
Okay.
to practice more.
Now, the next one was number 7. Number 7 was a bit more involved. So do you want to do that one? It's find the inverse of a matrix. You set it up perfectly, but once you set up, again, I think it was all came down to matrix multiplication, which I know you weren't here when we started, so you missed that part. So do you want to do that one, or you think you got it now?
I think I got the multiplication part down.
Okay, so are you okay with number 7? Like I say, you set it up well. You did A, which is 20 times 2003, multiplied it by x1, x11, x12, x21, x23. But then after that, you weren't doing your multiplication right. But if you've got that down now, you see when you did do your matrix multiplication, that would be 2x11 plus 0, because 0 times x21 is 0. So the top entry would be 2x11. Okay? that's going to be your first entry of the inverse matrix, 2x11. Then for your next entry, it would be first row times second column, would be 2x12 plus 0. Okay, so your next entry would be 2x12. Then your third entry, the second row first column, would be a 0x11, so that's a 0, plus 3x21. So your third entry is just going to be 3x21. You see that? So let me write those out for you. This is number 7. If you got it in front of you, you see what I'm talking about? Or not?
I don't have the paper in front.
Oh, you don't? Okay, I thought you still had it because you just sent me a copy of it.
Well, I can look it up on my email.
Okay. Do you think you're okay with it, or do we need to go on?
No, I think I understand the multiplication part better now.
But when you do that I'm just describing, doing the multiplication, this one's easy because of those 2 zeros in there. That makes it really easy. But when you get that answer, the answer of a product of A times its inverse is going to be the identity matrix. So that first entry is going to be 2x11. That's got to be a 1. So x11 has got to be 1/2. Okay? That next entry was your x2 times x12 has got to be a 0. So x12 has to be a 0. Then the next entry was
x21.
Okay, but it's the second row first column. That's a 3x21 has to be a 0, so x21 has to be a 0. And then the fourth entry was 3x22, because it's a 0, x12 plus 3x22 is equal to 1, so x22 has to be 1/3. So that answer we just got was 1/2, 0, 0, 1/3, I believe it was, wasn't it?
Okay.
Okay. When you worked it out, what we were doing, that's what you got. And then just take a look and see if you multiply that by 2003. This is just a quick check. I'm only going to do it one way, this way, just because I wrote the other one first. 1/2 times 2 is 1 plus 0. That's 1. 1/2 times 0 is 0 plus 0 is 0. That would be a 0. So I'm doing it fast, but okay. And then when you do the next one, 0 times 2 is 0, plus 1/3 times 0 is 0. That adds to be 0. And then 0 times 0 is 0, 1/3 times 3 is 1. And that adds to be it. Sure enough, that is your answer. Now that was pretty easy because your original matrix had a bunch of zeros in them. It makes everything a lot easier to do. But that is your correct answer. Now, number 11, you also said you needed help. Do you want to do that now, or you want to try that one on your own?
I'm going to try it on my own since
Okay.
it is same section.
Okay. And then 31, that was using the determinant to find it. Okay? Do you want to see that one? That's slightly different from what we have been doing. In fact, very different. You want to do that one?
Yes, we can.
Say yes?
Mm-hmm.
Okay. Number 31, same page. Here's 2, 3, negative 1, 5. That's your matrix. You're trying to find the inverse. I'll just say 2, 3, negative 1, 5. 2, 3, negative 1, and 5. All right. Now, this new technique, different technique, is using the determinant. So that's the first thing you do. I'm not going to write it down, but I'm going to put the double bars. That stands for determinant. Okay, normally you put an A in there or something, but didn't name it, so we won't name it. What is that determinant? You multiply the main diagonal, and this only works for 2 by 2 matrices, and this works. So you multiply the main diagonal, 2 times 5 is 10, and then you do the multiply these, but subtract it. Negative 1 times 3 is negative 3, but subtract that from 10. So 10 minus a minus 3 is 10 plus 3, and that's equal to 13. Now, why do you do that? Because the inverse of this starts off with 1 over the determinant. So it's going to be 1 over 13. Okay? That's how you do this technique. Now, the second part of this is the part that's a little squirrely, okay, but it works. Okay? Now, what you do, the matrix you put here is similar to this matrix, but only different. What you do is exchange the elements on the main diagonal. So you put the 5 up here, that's supposed to be a 5, and you put the 2 down here. Now for the off diagonal, or your anti-diagonal, or your other diagonal, you change the signs. So this becomes a negative 3. Now this seems mystical, magical, and change the sign of this one becomes a 1. So this is your inverse matrix, would be, I'm going to write it as a single matrix without anything in front. 5/13, because you multiply that 1/13 by every entry. 5/13, negative 3/13, 1/13, and 2/13. Now that's supposed to be your inverse matrix. Ooh, what a mess, okay? But does it work? How do we check? We do this one multiplied by that one. So I'm going to do it fairly quickly. You okay with that?
Yes, I'm okay.
Okay. Let's start with the 1, 1 entry. You know it's going to be a 2 by 2. We'll start with the 1, 1 entry. So it's the first row here by the first column here. Well, 2 times 5/13 is 10/13 plus 3 times 1/13 is 13/13. 10/13 plus 3/13 is 13/13, which is a 1. Hey, look at that. The 1, 2 entry here, first row, second column, okay? It's going to be first row here, second column here. 2 times a negative 3/13 would be negative 6/13 plus 3 times 2/13, that would be plus 6/13, minus 6/13 plus 6/13, 0. Then the 2, 1 entry here, the second row here, first column there. Okay? This will be a minus 1 times 5/13 would be negative 5/13 plus 5 times 1/13 is positive 5/13. Minus 5/13 plus 5/13, 0. Looking good so far. Let's see about that last one. The second row, second column. So you do the second row of this one times the second column of this one. So that would be a minus 1 times a minus 3/13. Minus times minus is plus. That would be 3/13 plus 5 times 2/13 would be 10/13. 3/13 plus 10/13 is 13/13, which is 1. Yep, you did it right. So this technique that works only with 2x2s, don't try it with anything else. 2x2s, first take the determinant. Now if that determinant is 0, stop right there. This matrix doesn't have an inverse. But if it's anything other than 0, that determinant, then put 1 over that determinant and then proceed. And what you do, what you multiply that by is another 2x2 matrix. This one, you just reverse the entries on your main diagonal, make that a 5 and a 2, and then change the signs of the two entries on your anti-diagonal, on the other diagonal. That's a minus 3 and a plus 1. And then multiply the constant in front by each of the elements here. There's your inverse matrix. You can check it by multiplying, and it better come up an identity matrix. Okay, does that make sense?
Yes, I understand better now.
Okay, good. Any others? And from anybody? Okay. Okay, I've got to find my page. There we go. So, any other questions? All right. If not, get that to stay in place. Let me see. I forgot to turn on my overhead light. In the early morning, sun comes in. This is a northeast exposure here. Sun comes in nice and bright in the east window. As the day rolls on, the sun moves around to the south side, and I get no direct sunlight, so I need a little bit of light here. All right. Now, my mark on my page has us in Chapter 2, Matrices, the inverse of a matrix, 2.3, which problems we were just doing, and we were doing the, I think starting at example 6, top of page 68. Is that where y'all had us starting? Yay or nay?
Yay.
Okay. I hear a cheer in the background. Yay! All right, good. I like people to be fired up. So let's do the inverse of the square of a matrix. Okay? Now, that might require a little bit of flip back one page, and let's see what the rule is. The inverse of a square of a matrix, that would be on the page 67, top of the page, just like number 2. A to the k inverse is equal to the same as A inverse raised to the k. Now, frankly, okay, it says do it 2 different ways. So I was going to say, I don't think it matters which way we do it. So let's do it. Here's what we're looking for, a to the minus 2. Now, that doesn't mean 1 over a squared, okay? That doesn't mean that, not in matrix talk, okay? Well, let's start with writing down what matrix A is. Here's matrix A. Okay? It's 1, 1, 2, 4. Okay, there's matrix A. Now what we're looking for is A to the minus 2. Now what does that mean? The minus sign means an inverse, and the 2 means a square. Okay? Now, that means one of two things. That could be interpreted this way. A inverse, the inverse of A, okay, squared. Okay, we'll talk on one there. The inverse of A, and then you multiply it by itself. Or the other way would be take the matrix A, multiply it by itself, that's called squaring it, and then once we have that, then we do the inverse of it. So let's do it both ways. Let's start by taking the inverse of A. Which technique would you like to use? Anybody have a preference?
I mean, it doesn't matter. We can do the A inverse of 2.
Okay.
The A with the power 2. The first one.
Okay, yeah, that's what we're going to do. How do you want me to do A inverse? There's a couple ways we could do. Augment this matrix with the identity matrix, do row reductions and go that way. Or we could do the new technique we learned, which uses a determinant. Which way you want to do it?
I think determinant's easier.
Yes, that's much easier. I'm all in favor. So how we begin this is find first the determinant of A. Now this only works for a 2 by 2, but we've got a 2 by 2, so let's take advantage of it. What is the determinant of A? Help me. 1 times 4 is 4, minus 2 times 1 is 2. 4 minus 2 is 2. Okay, there's the determinant. So what's the inverse of that matrix? It's 1 over the determinant. 1 over 2 times a slightly different matrix. And I want you to tell me what the entries of this slightly different matrix are. First entry?
1 over 2.
No. Okay, 1 over 2 is out front. What's the first entry here? Anyone remember? We just did it.
4.
4. Let's go to the bottom diagonal. What is it? 1. You reverse you reverse the main diagonal elements. Move the 4 up here, the 1 down there. What do you do with the second element here?
Under the 4, it will be a 2.
Now, under the 4 would be a minus 2. You negate the other two elements. So up here would be a...
And then it'll be a -1.
-1, you got it. So if we wanted to write this out just as a matrix without anything else, then we would do it as 1/2 of 4 would be 2. That's supposed to be a 2. The pen's not writing well. This will be a -1/2. And then this would be a -1. 1/2 of -2 would be a -1. And then 1/2 of 1 would just be 1/2. Okay? Now, there you've done A inverse. Now you want to double. You square it. So that means multiply it by itself. Okay? And itself was 2 -1/2. There's no easy way to do this. You just have to multiply them. -1, 1/2. Multiply it by itself. And of course, this is a 2 by 2. That's a 2 by 2. You can multiply them because the number of columns here is equal to the number of rows there. Wipe out those 2's and you have a 2 by 2. So your answer is going to be a 2 by 2 matrix. Of course it will. So I'm going to put my little blanks there. You don't have to unless you want to. To me, this just makes it easier to keep up with. Okay? And we identify this first blank. First row first column, so let's do it. 2 times 2 is 2 times 4 plus minus 1 times minus 1/2 times minus 1 is plus 1/2. So 4 is 8/2 plus 1/2 would be 9/2. Does everybody see that? Kind of an ugly number, but it's there. Okay? Now, first row, second column means you take the first row here again, multiply it by the second column here. So first row, by this, that'd be 2 times a negative 1/2 is a negative 1, plus a negative 1/2 times a 1/2 would be a negative 1/4. So that'd be negative 4/4 plus negative 1/4 is negative 5/4. Does everybody see that? I do my adding of fractions rather strangely, but it's easier for me to do them that way. Negative 5/4. Does anyone have any question on how we got that? Okay. The second row, first column, we'll do the second row here times the first column here. That'd be a minus 1 times 2, minus 2, plus 1/2 times a minus 1 is minus 1/2. Well, minus 2 is minus 4/2, minus 1/2 is minus 5/2. Okay, not really very pretty, but it's there. Okay, second row, second column would be the second row here by the second column here, and it's a minus 1 times a minus 1/2 is minus 1/2 plus, no, I'm sorry, plus 1/2. Minus times minus is plus. That's 1/2 plus 1/2 times 1/2 is 1/4. So that would be 2/4 plus 1/4 is 3/4. Now that's what we got doing A inverse squared. Now we're going to do A squared and then take the inverse of it. I like this a little bit better, I think, at least to begin with, because A squared is sort of easy to do. No fractions is what I mean. That's a 1, 1, 2, 4 times itself. That's what squaring means. Times a 1, 1, 2, 4. Okay. You can multiply them because they're both square matrices, same size. That'll give you a 2 by 2. You can go through the practice of doing it if you want to. I'll go on and put the blanks in. You don't have to do this unless you want to. To me, it just makes it a little easier. Okay. Sorry. I have what I think is a slightly pinched nerve, so I have to wander around some. I have to move my legs, otherwise my knee starts aching. All right. So this is the 1 entry. So I'll take the first row here times the first column there. 1 times 1 is 1, plus 1 times 2 is 2. 1 plus 2 is 3. See, this multiplication is a lot easier. They're whole numbers. This entry is the what entry? Anybody?
1, 2.
1, 2 entries. So we take the first row here times the second column here. 1, 2. And you tell me what it is.
One times 1 is 1. Plus 2 times... plus 1 times 4.
Yeah.
It's 5.
Okay, 5.
Not bad.
Okay. We had to wake James up there. Okay. I think we got him now. Okay. Now, what is the address of this entry?
221.
21. So we take the second row here by the first column there. And that would give us
2 and 1 is 2.
right.
4 and 2 is 8. So you get 10.
10. Looking like a big number, isn't it? Okay. And then this entry here is the
2-2.
2-2. So we take the second row here by the second column here, and that would be
2 and 1 is 2. 4 and 4 is 16. That gives you 18.
Goodness, what big numbers we have, Grandma. Okay. Okay. Now, we have done the a squared part. That's what we just did here. Now we need to take the inverse of this one. What technique would you like to use?
Determinant.
I would like that too. And what's the determinant of that one?
18 times 3
Is?
minus 10 times 5.
Okay, so first do 18 times 3. What's that?
54.
54 minus?
50.
Which is?
4.
4. Okay. Good math today. Okay. Now, so to get the inverse of this, how would we start?
A inverse equals 1 over the determinant.
Which is?
1 over 4.
1 over 4. So it's 1/4 times a slightly different matrix here. What matrix do I write here?
18.
18 is the first entry. Let's go down to the last entry.
3.
3. Okay. Let's go to the second entry.
-5.
-5. And the third entry?
-10.
-10. So, let's see what we get. 18 over 4 is 9/2, isn't it? -5 over 4 is -5/4. -10 over 4 is
-5/2.
-5/2, if I could write. That's the 5 there. Okay. And 3 over 4 is
3/4.
3/4, if I could write. Okay. Let's see how these compare. Oh my goodness. 9/2, 9/2, -5/4, -5/4, -5/2, -5/2, and 3/4, 3/4. Yes! What they told us is true, or at least it appears to be true, that a to the -2 is either a inverse squared or a squared inverted. Okay? Either way, you get the same answer. And let's see how the book did. Oh my goodness, they got it right too. Good for them. I'm really proud of them, aren't you? Okay. Both ways. Now, let me ask again, do you all have your books? Anyone not have a book today? I take that means everybody has one. Okay? Well, then I won't bother writing this down, but let me show it to you because I know you see it, but this way it'll be out there. There it is. Here is theorem, can't read the number, 2.5, no, 2.9. Theorem 2.9. The inverse of a product. I think we've already done this. We had the others there, but we didn't do this one. So let me read it to you because I can't read upside down, backwards. And talking to the microphone too. If A and B are both invertible matrices. Now what does that mean? It means several things. Number one, they're both square matrices. Gotta be. Okay? And, excuse me. Wait. My throat's closing up on me. In between classes, I went down and ate a few salted roasted almonds just to get me through because this is my hunger time right now. And I think I got a bit dry. Sorry about that. So A and B are invertible matrices, meaning they're both square matrices. Okay? They both have inverses. A inverse exists, B inverse exists. Okay? Now, for this to be working, they have to be the same size. So they say it this way, of order n. They're both n by n matrices. That could be 2 by 2. It could be 7 by 7. It could be 85 by 85. It could be any square matrix, but they have to both be the same size. Or if they're both invertible, then their product, AB, is guaranteed to be invertible. And the product, by the way, will be the same size, n by n. Okay? And not only that, is that product invertible, but here's what its inverse is. This I think I will write down, because this is the conclusion. Okay? So, we've got that A and B are both invertible. That means they do have inverses. Okay? That means A inverse and B inverse both exist. That's what it means for those to be invertible. Both inverses exist. Okay. Now, what the theorem tells us is that the product of those two matrices, AB, which will also have to be and by the way, they're n by n matrices, so order n. I'm just going to put n there. Order n, both of them. AB is also an order n. It's also invertible, so its inverse, this is invertible, so its inverse is equal to, now get this is the sort of strange part, but we've seen this pattern before. It's B inverse times A inverse. So we don't just do inverses of each other. That's a 1. It's an ugly one. Let me see if my eraser is working now. My last class, it just quit working on me, and it's happened in several classes that way, and it erases the wrong thing. There we go. That's supposed to be a -1. Okay, so that's the bottom line here. Not only is the product of two invertible matrices also invertible, but its value is the second inverse times the first inverse. Okay? Strange but true. Now, they have a little proof here, and it is a pretty nice and decent little proof. And it's saying that these are that AB, the inverse of AB is equal to this. So let's take AB. Remember, they're all the same size matrix, n by A, and multiply that by B inverse A inverse. Now, if indeed these are inverses of each other, That's what the assumption is, that they're inverses of each other. Your result should be the identity matrix. Well, if B has an inverse B inverse, then the product of that is the identity matrix of size n. And then you multiply that by A, and you get A. Okay? Because you multiply any matrix by the proper identity matrix, you're going to get the same matrix. Then take that and multiply it by A inverse, and because those are inverses of each other, that guarantees you that you're IN. So sure enough, the product matrix times the reverse inverse products, okay, those are inverses of each other. That's how you prove that. Now, what that theorem states is that the inverse of a product of two invertible matrices is the product of their inverses in reverse order, okay? And that can be generalized to be any size products. If A1, A2, A3, A4, A5, all these A's, as many as you want to, up to A sub n, if they're all invertible matrices, then what is the inverse of the product of all those matrices? Well, the inverse of the product would be A sub n, A sub n inverse times A sub n minus 1 inverse, so A to the n minus 2 inverse, all the way down to A sub 3 inverse, A sub 2 inverse times A sub 1 inverse. And that's exactly what your statement at the bottom of the page is saying. You can extend that theorem that we did there to be any number of products. To get, if all those are invertible matrices, then the product of all those invertible matrices is the product of their inverses in reverse order. Okay? And that gives us that. So let's move to example 7, top of page 69. So I'm going to clear this screen, if I can get my cursor to show up. There it is. Okay? And let's do this one. All right. Here's matrix A. And they're not nice to us any longer. Here's matrix A. Well, they could be worse, but it's not as nice as they were. 1, 3, 3. 1, 4, 3. 1, 3, 4. Okay. Sorry, folks. Hunger is setting in. Okay. Here's matrix B. One, two, three. One, three, three. Add 2, 4, 3. Okay, that last one's a 3. Okay. I'm beginning to regret not bringing up a soda or something because hunger is really grabbing at me right now. Sorry about that. Not your problem. Okay. Now, they cheat like crazy. Okay? What they do is just tell you what the inverses of these two matrices are. Since we're really new at this, I think we need to do them ourselves. So we need to do what A inverse is. Now, does anyone remember what the procedure for getting A inverse? Now, if this was a 2 by 2, that's why I said they're not nice to us anymore. If this was a 2 by 2, that would be easy. It's not. Here's how we find the inverse of A. And this is the only technique we have right now. You write down A, 1, 3, 3. Augment it by the identity matrix of the same size. And that would be 1, 0, 0. Second row, 1, 4, 3. Second row of the identity matrix, 0, 1, 0. Goodness, my throat's. Okay, that last one's a 0. That didn't help much, did it? Third row, 1, 3, 4. That's a 4, ugly 4. Last row of the identity matrix of that size is 0, 0, 1. Okay. Now, what's the first thing you want to happen? What we're going to do is a row reduction. Okay?
You want a 1 in the upper left-hand corner.
Bingo, bingo. Oops, I can't say that in Alabama. We got it already. So we're happy campers. What do we want after that?
Zeros below the 1.
Okay. So how do we get this first, the second 1 here to become a 0?
Multiply -1 times row 1 plus row 2.
Got it. Negative row 1 plus row 2. All right. Now, since we're using row 1, we write it down. 1, 3, 3, 1, 0, 0. I'm going to regret doing this, I'm certain. Okay? So we do what it tells us to. Minus row 1 plus row 2. So minus 1 plus 1 is a 0. Minus 3 plus 4, thank you very much, is a 1. Minus 3 plus 3 is a 0. It's really coming out well. Minus 1 plus 0 is a minus 1. All right. Minus 0 plus 1 is a 1. And minus 0 plus 0 is a 0. Okay. Goodness gracious. Wait just a moment. Sorry. My eyes are getting so dry. I think maybe part of the problem is the ceiling fan being on. Let me turn it off. I'm going to try something else too. My wife gave me these yesterday. I'm sorry, it'll rattle around in my mouth, but I'm going to put a Mentos in. And maybe that'll help my throat a little bit. Okay. What are we going to do to get this one to become a 0?
Same thing.
Yeah, pretty much, except it's going to be minus row 1. This time plus row 3. So not quite the same, but close. Same procedure. Row 3. Okay, let's do that. Minus 1 plus 1 is?
0.
Good. Minus 3 plus 3 is?
0.
0. They were fairly nice to us. Minus 3 plus 4 is a?
1.
1. They were very nice to us. Minus 1 plus 0 is?
Minus 1.
Minus 0 plus 0 is?
0.
And minus 0 plus 1 is?
1.
All right. They were kinder than I thought. Let's take a assessment of where we are. We've got a 1 here, 0 is below. Yes, right? We got a 1 here. All we need is a 0 above. We've already got a 0 below. So let's take care of that first. How do we get this 3 to become a 0?
Negative 3 times row 2 plus row 1.
Perfect. Okay, is everybody following what we're doing? Okay. Sorry about the rattling in my mouth, but it is helping my throat. Right, since we're using row 2, we write it down. 0, 1, 0. By the way, that's exactly like we want it to be. Minus 1, 1, 0. Okay. We're doing what they told us to here. Minus 3 times row 2, minus 3 times 0, of course, is 0, plus 1 is 1. Good, we didn't want that to change. Then we have a minus 3 times 1 is minus 3 plus 3, that's a 0. That's exactly what we wanted it to do. And then we have a minus 3 times 0 plus 3 would be 3. Then we have a minus 3 times a minus 1, which would be plus 3, plus 1 would be 4. So 4 there, okay? Then we have minus 3 times 1 would be minus 3 plus 0 would be a minus 3. If I could get the pen to write. There it goes. And then we have a minus 3 times 0 is 0 plus 0 is 0. Okay. Now, we already have a 0 here, so let's write down row 3. 0, 0, 1, minus 1, 0, 1. Okay. A quick review. What did we want? A 1 here. We got it. What next? 0 is below it. We got it. What next? Leading 0 entry in row 2. We want it in column 2. That's where it is. A leading 1. 0 is above and below. Excellent. Then in the third row, we want the leading non-zero element, preferably in column 3 to be a 1. We got it. We want zeros above it. We got 1 0 above it. All we need to do is get that 3 to become a 0. And how do we do that? Minus 3, the row we're working with, that leading 1, row 3, plus row 1, the one we want to change, that becomes the new row 1. Okay, let's see if we can squeeze in our final matrix here. Okay, we're using, well, second row is just like we want it, so let's just write it down. I'm not going to change anything in it. That's a 0, 1, 0, because that's basically your identity matrix, row 2, and then minus 1, 1, 0. All right. The third row is the one we're using, so you don't want that to change, and that's first 3 elements are the identity row elements. That would be a minus 1, 0, 1. Okay, now we work with the first row. Minus 3 times row 3 plus row 1. Minus 3 times 0, 0, plus 1 is 1. Minus 3 times 0, 0, plus 0 is 0. Good, we didn't want that to change. Minus 3 times your 1 is a minus 3 plus 3. That we did want to change to become a 0, and sure enough it did. Now, minus 3 times a minus 1 is a plus 3 plus 4 is 7. Wow, what a big number for all the rest of them to be plus or minus 1. The next one is minus 3 times 0 is 0. Minus 3 is minus 3. And finally, minus 3 times 1 is minus 3 plus 0 is minus 3. Okay, if we've done everything right, A inverse is now that what used to be the identity matrix, it's become the inverse matrix. And what was the original matrix has become the identity matrix, and sure enough that is. So the inverse matrix will be 7, negative 3, negative 3, strange, unusual row, negative 1, 1, 0, and negative 1, 0, 1. Okay, goodness gracious. Talk about tedious. Now, if you were really gung-ho about it, James, you could multiply this matrix by that matrix and see if you get the identity matrix. I sure hope you do, but since I'm not quite as gung-ho, I'm going to look in the book and see what they got. 7, negative 3, negative 3, negative 1, 1, 0, negative 1, 0, 1. Yes, they did. Okay? Now, hopefully that's enough. Or do you want to see B inverse done the same way? Help me, somebody. You want to see B inverse done, or you want to take their word for it? What you want to do?
I don't, but I don't know about everybody else.
Okay.
No,
I'll take their word for it.
Yeah.
Okay. All right. They're going to trust the book now. Boy, famous last words. The book has it B inverse, and somehow they acted like you're supposed to know this, and you don't. You aren't. They just didn't want to do the derivation of it. They're claiming, and we'll take their word for it because we're trusting souls like we are, is 1, negative 2, 1. Negative 1, 1, 0. And 2/3, 0, negative 1/3. Now, if you're expecting anything to be obvious and that, oh, let's just write it down. No, don't even guess it. These things follow no pattern. I wish there was. It's just you have to do the whole work. Okay. Now, the original problem said find AB inverse. This is what we're looking for now. A, B, inverse. And they put that in parentheses, I'm pretty sure, because otherwise it's ambiguous. Now, the book also tells us there's two ways to get it. One way, of course, is to multiply A times B, matrix multiplication, and then do what we just did, find the inverse by row reduction. A times B, that's not too bad, but it's matrix multiplication 3 by 3. But then finding the inverse is just like we did here, with no promises that it will be quite that easy, if you thought that was easy. But the other way to get the inverse is to use the identity they just told us, that this is equal to, anyone remember what it is? B inverse times A inverse. Now, just between you, me, and the fence post, this way you'd have one matrix multiplication to do and then an inverse matrix to do. And this side, all you have to do is one matrix multiplication. Which way you want to go? One step or two steps?
One step.
I agree. So let's write down A inverse again. Either way, you got to do a matrix multiplication. This is all you have to do. The other way, you have two steps. Do the multiplication, then do an inverse, which is even a longer process. So let me write down A again, or A inverse. That's supposed to be a 7. Negative 3. Negative 3. Negative 1. 1. 0. And negative 1. 0. 1. Okay. We're going to do a product. So let's go down here and do it. Now I'm going to go through all the standard questions that I always ask, and I think you know the results. Can you multiply these two? This is a 3 by 3 by a 3 by 3. The two inner numbers are both 3's, so wipe them out. Your answer is going to be a 3 by 3. We should know that. Okay, so this is going to be a 3 by 3. All right, meaning 3 columns and 3 rows. And again, how we do this, find the address and then do the operations according to that address. So what is the address of this first place?
1, 1.
1, 1. First row, first column. And since we're doing inverse order, B inverse times A inverse, that's how I wrote it that way. We do first row of B multiplied by the first column of A, adding as you go. So that's 1 times 7, 7, minus 2 times minus 1, plus 2, that's the 9, and then 1 times minus 1 is minus 1, that leaves us an 8. Agreed or not?
Agreed.
Okay, good deal. Next, we'll do the 1, 2 entry. First row, second column, so we do first row of B, since it's the one that shows up first, times the second column of A. Okay. Sorry, wait just a second. Mentos did help my throat, but it left sort of a strange taste in my mouth, so I'm trying to wash some of that out. Okay. So, first row, second column. All right. See, if we were in class, you'd see my hands doing like this. And that's much easier than here, but these don't have but one cursor, so I can only do one at a time. That's going to be 1 times a minus 3, plus a negative 2 times a 1, so negative 2, so minus 3 minus 2 is minus 5, and then this one's going to be a 0. So that looks like a minus 5 to me. All right. Now, first row, third column, be first row of B, third column of A, or A inverse, okay. 1 times a negative 3, plus 0, I can do that one, plus 1. So negative 3 plus 1 is negative 2. Agreed? Okay. Now, second row, first column. It means the second row of B inverse times the first column of A inverse. It's going to be negative 1 times 7 is negative 7, plus 1 times negative 1 is minus 1. That gives you a minus 8, and then that one's going to be a 0. So this is going to be a minus 8. Interesting, but true. Looks to be true anyway. All right, the 2, 2 entry. Second row, B inverse, second column of A inverse. Minus 1 times a minus 3 is a plus 3. 1 times 1 is 1, so 1 plus 3 is 4, and then a big fat 0. So that seems like a 4. Okay. All right. I sure wish I'd have brought up a soda now. I'm almost out of water. The 2, 3 entry here. Second row of B, B inverse, third column of A inverse. Minus 1 times minus 3 is plus 3. And then you get a 0 here and a 0 there. So that's just a 3. Now we're down here in the third row, first column. That means the third row of B inverse, first column of A inverse. Oh boy, the ones we've been waiting for. 2/3 times 7 is 14/3. Agreed?
Yes, sir.
Okay, plus 0 times that would be 0. So we're still with 14/3. Minus 1/3 times a minus 1 is a positive 1/3. So 14/3 plus 1/3 is 15/3, which I think comes out to be a 5. Do you think so, the same thing?
Yes, sir.
All right. Now the 3, 2 entry, third row of B times the second column of B inverse, the second column of A inverse. Okay? All right. 2/3 times minus 3 will be a minus 2, plus a 0 from here and plus a 0 from there. I think it's just a minus 2. Concur or not?
Concur.
Good. Now the 3, 3 entry here will be the third row of B inverse times the third column of A inverse. It starts the same way. 2/3 times a minus 3 is a negative 2. Plus a 0. 0 times 0 is 0. So negative 2 minus, 1/3. So that's positive 6/3 minus 1/3, I believe comes out to be 5/3. Agreed or not? Whoa, that's ugly. So bizarre. All integers except that last entry is a 5/3. Let's see what they got.
Shouldn't it be a minus 5/3?
Yeah, wait a minute. You're probably right. Yeah. It's probably even worse than that. I was so eager to have it over with. This is a minus 2, and then we have a minus 1/3. So minus 2 is minus 6/3. Minus 1/3 is minus 7/3. So James, you really blew that, you know. I don't know what's wrong with you today, okay? That's a minus 7/3. Okay. Thank you. A minus 7/3. I was just so ready for that problem to be over with. Okay. And that is indeed, let's see if we got them all. 8 minus 5 minus 2, got it. Negative 8, 4, 3, got it. 5, negative 2, negative 7/3, James. We got it. Now, there was example 7. Can't wait till 8, can you? Okay, never mind. One important property in algebra of real numbers is the cancellation property. It seems like we've been here before, doesn't it? That is, if you have AC equal to BC, then you say, well, A has to equal B, because divide out C from both sides and you get A equal B. Okay? Invertible matrices, not all matrices, but invertible matrices have similar cancellation property. Earlier, we said just any old two matrices do not, but invertible matrices do. So here's theorem 210. And again, I hope all of you have a book. And if you do, you can look on page 69, just below the middle of the page. If C is an invertible matrix, got to be invertible, okay? C is an invertible matrix, then the following properties are true, okay? Now, I think I will clear this. Any objection to my clearing this? No objections? It went. So C is invertible matrix. Now that tells you two things right off the top. C is invertible. Okay. Two things you know right off the top, C has to be square. You cannot talk about invertibility with anything other than a square matrix. So C has to be square. And the second thing, of course, that tells you is that C prime exists. So, and it's also square, by the way. I mean, not C prime. C inverse exists. Okay? So it's invertible. That means there is a C inverse. Okay. That's all the givens in this problem. Now, here is the first. First property. Okay? If A times C is equal to B times C, notice they're written in the same order. Okay? The C coming at the end. If A times C is equal to B times C, that implies, beyond the shadow of a doubt, that A has to equal B. Okay. Now, let's hit some things here. Is there any mention about either A or B being invertible? No. Is there any mention about either A or B being square? No. All that's required, you know C has to be square. Okay? Now, so let's call it n by n. So all that we need to know here is that A, sorry, I can't talk. A must be some m by n. And their product is then going to be an N by N, M by N. Well, guess what? B also, in order for the product to be an M by N, B must also be an M by N. So number one, A and B have to be the same size. Now to multiply, all B has to be is some P by N. But the thing is, then that product would be P by N, and if P and M were not the same, they couldn't be equal. So you know that A and B are the same size. Now, it's a fairly easy proof to do. Since this product is going to be an M by N, I'm sorry. I'm so sorry. I can't. I'm completely out of water and my throat is going on me like crazy. If C is an N by N, C inverse also has to be an N by N. That's understood. So you could multiply both sides of this by C inverse. Okay, right? Well, C inverse times C inverse is I. C inverse times C inverse is I. And guess what? That would leave you A times I is equal to B times I. That would be A is equal to B. So that was really easy to prove, and that's exactly what they do after this one. Here's the second principle or property. If C is an invertible matrix. If CA is equal to CB, that was my uncle's initial, okay? He was also a Charles. He was Charles Bain, okay? Okay. Now, if that's true, now what does that mean? Remember, C is N by N. That means A has to be an N by something else. N or M or P or whatever, but it has to be, let's just call it M. Okay? So the product will be an N by M. Well, then if those are equal, that means B also has to be an N by M. So its product with C will be an N by M. Well, this time, you'd multiply both sides on the left by C inverse, and then you'd have I times A is equal to I times B, and that implies, of course, that A is equal to B. Now, earlier when we said this wasn't necessarily true, that's because we were dealing with non-invertible matrices. If that common matrix is invertible, and these are the same sizes, well, and the equality holds, yeah, you got it. Now, be sure to remember that Theorem 210 can be applied only, I've said this before, when C is an invertible matrix. If C is not invertible, then this does not work. Okay? Example 5 in section 2.2, we just did that, and you saw they weren't. And the reason was the C in that problem was not invertible. So guess what? If the products don't match, if the products match but the matrices don't, you can guarantee C is not invertible. Now, we're moving now to, again, systems of equations. For square systems of equations, those having the same number of equations as they have variables, square systems, you can use the theorem below to determine whether the system has a unique solution. So here is the theorem. Now, y'all have your book. I think I'll hold this up into the camera so you can see it, but you have your book. Here is theorem, what is that? 2.11. Okay? And that's this. If A is an invertible matrix, has to happen, of course that means it's a square matrix and it has an inverse, A inverse, then the system of linear equations AX equal B also has a unique solution, x is equal to A inverse times B. This is another reason we do the inverses. If that coefficient matrix turns out being invertible, then you can solve it just by doing that. Okay? So again, let me just write that down. A is invertible. That's given. And that's the only thing given. Well, let's see if it is the only thing given. If A is an invertible matrix, now that guarantees A has to be square, remember, and the A inverse exists, okay? Then the system of linear equations, now this is also guaranteed. A, X equal B. Okay? If that A is an invertible matrix, that means that any system of equation with this, an invertible matrix as its coefficient matrix, no matter what B is, that's going to be a consistent system. Okay? It's going to have a solution. Now, if B's were all zeros, then the only solution is going to be your trivial solution. X has to be zeros. All the components of X is zero. But if B is anything else, then your unknown X, and that's usually written as a vector. I didn't write them as vectors, I should. Both of these are column matrices. You can also do as a vector. And you can just write down the answer now, so to speak, would be A inverse times B. And that's usually not a hard calculation to make. The hard thing is to find the inverse. So if you can find that inverse, then change your B. Don't mess with changing the inverse. It's the same. And you can just calculate the various X's that will produce with those B's. Okay. Now, also, that solution is unique. Okay? And the reason that's unique is because if there were two solutions, you could apply a cancellation property and you basically wind up that x1 has equal x2, so they're not two different systems. All right. Now, so what? One use of this theorem that we've just been talking about here is in solving several systems of equations that have the same coefficient matrix. So let's say you're a manufacturer and you have so many devices and input, manpower, capital, whatever. Everything's the same, but you want different outputs, okay? You want B because your orders, this happened to be 1 month, is going to be B. So what do you need to do with your variable matrix? That's how many people, how many whatever, you're doing. Once you figure that inverse matrix once, and remember, it's sort of a long process, but once you get it once, you calculate the inverse, multiplying that by the vector B is really a piece of cake. So then you can come up with what kind of inputs you need for that month. Then the next month your orders are different. Use that same invertible matrix, but your output is going to be different. Your B's are going to be different. Just multiply that same inverse matrix by your new B. That gives you new X. Okay? And it's easier if you have multiple applications of the same coefficient matrix. This is the faster way to go. Otherwise, Gauss-Jordan is easier. Okay? If you're going to change the matrix every time, then use Gauss-Jordan. If you're going to keep the same matrix every time, do one time of finding the inverse, and then after that, it's so much easier to do it this way. So, here's example 8. I'm going to clear my screen because this looks like this could take a bit. Okay. It's going to take a bit just to write it down. And we go to 1:15, so we've got a half hour, a little bit more. Okay, 2x plus 3y plus z is equal to -1. My business application, that wouldn't have made much sense. 3x plus 3y plus z is equal to +1. And 2x plus 4y goodness, I'm hungry, plus z is equal to -2. All right, now, if you don't mind, I'm going to be real lazy, okay? Look at the B part of this problem. 2x plus 3y plus z, same coefficients, is equal to 4. So here I'm just going to write 4. Next equation, 3x plus 3y plus z, same equation, that's equal to 8. And the third equation, 2x plus 4y plus z, same coefficients, that one's equal to 5. Okay, the C part, 2x plus 3y plus z is equal to 0. 0. 0. All three of the equations are the same except for the constants. Okay. Now, I wonder if that coefficient matrix looks a little bit familiar. I was hoping it was, but unfortunately it's not. Okay. I was thinking that example 7 we did was similar, and it was similar, but not quite the same. Okay? Yeah. So what we've got to do, and this is a bear of a problem in some senses, because of just the numbers. So let's deal with that coefficient matrix. And they call this matrix A, their favorite name for a matrix. Okay, that's going to be 2, 3, 1. 3, 3, 1. Goodness, I'm having trouble even focusing. 2, 4, 1. Okay. going to be tough. Okay. Now, here's what makes this one especially rugged in my mind. I asked myself, why couldn't they have made the Z the X and the X the Z? If they'd have done that, we'd have had a leading one in the upper left. They didn't do that. Now, if you kept up with things and made sure about it, we could flop that around, but they haven't told us we can do that yet. So, not going to do that. So the next thing I look for is any of these rows, can I divide by that leading thing and get it? In the first row, if you divide everything by 2, you wind up with 3 halves and 1 half. Okay, 2 fractions. Second row, if you divide everything by 3, you get a 1, 1, 1/3, 1 fraction. If you divide the third row by 2, you'll get 1, 2, 1 half. Now, frankly, between UV and the fence post, I like the third row better. So what I'm going to do, my first act is going to be 2. I'm going to exchange the first and the third row, and at the same time, I'm going to divide the third row by 2. So my new matrix, and I hope you're okay with me doing 2 steps at once. I just don't want to have to write all these things together. Move the third row up top, and that's going to be a 1, and divide by 2, 1, 2, 1 half. I'm real tempted to call it 0.5, but I'll keep it at 1 half. And then it doesn't matter how you leave the next 2. I'm going to go on and do 3, 3, 1, and 2, 4, 1.
It's 2, 3, 1, isn't it?
You're right. I'm about to lose it, folks. Thank you. There we go. Okay. 2, 3, 1. We exchanged the first those 2 rows. Okay. Oh my. It seems like such a burden just writing down. Okay. Now we're ready to start our row reductions. Okay. We got the 1 here, finally. It was sort of difficult, but we got it. We want zeros below it. So the first one will be -3, row 1, plus row 2. I can tell James is all way ahead of me already. He's already got the whole thing worked out. Okay. Okay. First row is still 1, 2. We don't change the first row because we're using the first row. We're using that leading 1. Okay. Oh, wait a minute. Wait a minute. We're not just doing a row reduction. We're also looking for an inverse. Sorry, folks. We should have augmented that first matrix with the identity matrix. So I'm going to have to go back and do this. This is really doing multiple steps at once. Okay? And sorry about this, but we got to do it. Okay. Now, let's go back and see where we came from. We were using this row here. Remember, it was augmented by a 0, 0, 1. But then we divided by 2. So now its augmentation is a 0, 0, 1 half. Right? Now,
yes, sir.
Say again?
Yes, sir, it is.
Okay, you got it. Okay. thought you were saying, no, you didn't understand it, and then I was going to have to explain it better. And that was going to be tough. Okay. Now, remember, second row remained the second row, but we're doing this to it. So minus 3 times 1 is minus 3 plus 3 is 0. Okay? That would be a minus 6 plus 3 is 3. And this becomes a minus 3 halves plus 2 halves would be a minus 1 half. Aren't you loving this problem? Okay.
Shouldn't that 3 be negative 3?
You're right, negative 3, I think. I may have even said it, but wrote it wrong. Okay, I don't remember what I said. Yeah, negative 6 plus 3 is negative 3. All right, now we've got to do our imaginary row there, okay? This is that first row. That's a 0. So it's a minus 3 times 0 plus, and the first entry here was also a 0, so that stays a 0. Now, the next was a minus 3 times 0 is a 0 plus 1, and that stays a 1 because that was our next one. But then the next one's a minus 3 halves plus 0 would be a minus 3 halves. I hope I'm doing it right. Okay, because remember we have the imaginary 0, 1, 0 following that. Now, remember this has the imaginary 1, 0, 0 following it. So let's do what we need to hear. We do minus 2, row 1, plus row 3. Okay. So, minus 2 times 1 is minus 2 plus 2 is 0. I can do that one without making too many sign errors. Okay. Minus 2 times 2 is negative 4 plus 3 is a negative 1. Okay. Minus 2 times 1/2 is a minus 1 plus 1. That's going to be a 0. I see a swapping of 2 rows coming up, don't you? Okay. And a minus 2 times 0 is going to be 0 plus 1 is 1. And a minus 2 times 0 is 0 plus 0 is 0. And then a minus 2 times a 1/2 is a minus 1 plus 0 is a minus 1, I think. Please tell me I'm okay.
You're all good.
Say again? All good? Thank you. All right. Now, guess what? I'm going to swap 2 more rows and change signs of this one because that's exactly what I want in row 2, except for the minus 1. So here's what we're doing next. We're exchanging rows 2 and 3, but also negating what was row 3 will be the new row 2. Top row stays the same. 1, 2, 1/2. 0, 0, 1/2. Okay. Middle row was the bottom row, but multiplied by minus 1. So that's going to be a 0, a 1, a 0, a minus 1, a 0, and a 1. Okay? And the bottom row stays pretty much like it was before when it was row 2. Minus 3, minus 1/2, 0, 1, negative 3/2. This is getting ugly, isn't it? It's been ugly. I love this problem, don't you? Okay. Now, let's review what we've got, where we are. 1 here, 0 is below. We got a 1 here by manipulation. We want a 0 above and a 0 below. Okay? So, what we're going to do here is minus 2, row 2, plus row 1. Right?
Yes, sir.
Okay. So let's go down here and write it. Okay, we're using row 2, so I'm going to fill that in. 1, 0, negative 1, 0, 1. New row 1. Minus 2 times 0 is 0, plus 1 is 1. Exactly. Wait. You said I was right, and I wasn't. This is a 0. Oh, yuck. All right. Let's get this cleaned up. I don't have enough numbers there. I left off that leading 0 is what I did. Okay? So this is going to make it really hard to fit everything in. 0, 1, 0, minus 1, 0, 1. I had the right numbers, I just left off my leading 0. Okay, so let's go again. Minus 2 times 0 is 0 plus 1 is 1. Minus 2 times 1 is minus 2 plus 2 is 0. That's exactly why we did it. That's what we want it to be. That's a 0. A minus 2 times 0 is 0 plus 1/2, still a 1/2. Minus 2 times a minus 1 is plus 2, plus 0 is 2. A minus 1 times a 0 is a 0, plus 0 is 0. I can do that one. That's lots of nothing. And then minus 2 times a 1 would be a minus 2 plus, that's minus 4/2 plus 1/2 is minus 3/2. Right? Please say yes. Minus 2/2, which is 4/2. Let's see, 4/2 plus 1/2, minus 3/2. All right, down here is going to be a 3 times row 2 plus row 3. All right, that's what we're going to do now. 3 times 0 is 0 plus 0 is 0. Good, we didn't want that to change. 3 times a 1 is a 3 plus minus 3. That's a 0. We did want that to change exactly that way. And then we had, if y'all can read this, 3 times a 0 is a 0 minus 1/2. Is that what that's reading? I think it is. You've written better than I have. Is that a minus 1/2 there?
Yes, sir.
Okay, good. And then we have a 3 times a minus 1 is minus 3 plus 0 is going to be minus 3. And then we have a 3 times 0 is 0 plus 1 is 1. And 3 times 1 is 3, which is 6/2 minus 3/2 is going to be 3/2. Do y'all get that too?
Yes.
All right. Now, the only thing I'm having some really serious problems with is that, isn't this a 1/2 here? I think I wrote it as a 1/3. I think that's a 1/2. isn't it?
Yes, sir. 1/2.
Okay, I'm sorry. I couldn't read my own lousy writing. I know you find that hard to believe. Because you love reading my lousy writing, don't you? Okay. Now, what's the next thing you want to happen? Let's do a quick review. We have a 1 here, 0 is below, leading 1 here, that's right where we want it, 0 above and below, well, fantastic. Next thing we want to happen is that, I think that's a negative 1/2, we want to become a positive 1. So what are we going to have to do?
Multiply by -2.
Yes, multiply by -2. So -2 times row 3. And that's just going to be the new row 3. All right. So it's a lot of writing for just that to happen. In fact, is it all right if I just erase and fill in what it is? Will y'all be okay with that? Because we're running out of time.
Yes, sir.
That'll be a 0, that'll be a 0. -2 times -1/2 will be a positive 1. So I'm going, as long as my eraser will work, that will be a +1. Okay. Okay. And a -2 times a -3 will be a +6, right? Correct me if I'm wrong. +6. Okay. -2 times 1 will be a -2. I'm only erasing one at a time because I can't remember what they are. -2. And a -2 times a 3/2 is going to be a -3, right?
Yes, sir.
So let's see. A -3. So -2 and a -3, I hope. Did I write them right? Okay. That saved me a lot of writing. Thank you very much. Now, last step. We got a 1 here, 0 is below. 1 here, 0 above and below. And a 1 here, which is just what we want, leading 9 entry 1. How are we going to get, what we want is a 0 up here. How will we get that 1/2 to become a 0?
-1/2 times row 3.
-1/2 times row 3. I can't write. And add it to row 1. If you can read that, good luck. Okay. Now, we're not going to change row 2. 0, 1, 0, -1, 0, 1. We're not going to change row 3. 0, 0, 1, 6, -2, -3. I'm going to time out for just a second here. Yes, so far so good. All right, now we're going to do what we said we were going to do. -1/2, row 3, -1/2 times 0 is 0 plus 1 is 1. Okay? -1/2 of 0 is 0 plus 0 is 0. I can handle that one. -1/2 of 1 is -1/2 plus 1/2 is 0. Okay. -1/2 of 6 is -3 plus 2, I believe, is a -1. Concur?
Concur.
All right. Next one, minus 1/2 of minus 2 is a plus 1. Plus 0, I think, is a plus 1. Okay? And finally, one we've been waiting for. Minus 1/2, and if my understanding is right, that's a minus 3. That's a positive 3/2 plus a negative 3/2. I think it's going to go to 0, isn't it? Could that be? No, it isn't. How did I mess up that last one?
Should be a positive 3/2.
Okay, you're right. Positive 3/2. Okay. That's a positive 3/2. And that up there, is that supposed to be a positive 3/2?
Yes, sir.
Oh, I'm sorry. Well, why didn't you tell me? Okay. So positive 3/2 plus 3/2 is positive 3. Okay. And that, no, it isn't. It was a 0. I had it right.
I wonder how I got a positive 3/2 then.
What's that?
I must have did something wrong.
Okay, well, I'm doing lots of things wrong. Okay. That I thought was a negative 3/2. And sure enough, when you add a positive 3/2 to a negative 3/2, you get a 0. And that's, well, I looked in the book and looked in the wrong place. Yeah. It's a negative 1, positive 1, 0, negative 1, 0, 1, and 6, negative 2, negative 3. This is your A inverse. I'm just going to do it like this and call this A inverse. Now that was a lot of work to get it, but frankly, it was worth it. Because now if we want to solve this first system here, where that's equal to minus 1, 1, 2, all you do is take the A inverse and multiply it by negative 1, 1, negative 2. That's not that hard to do, because what you do, this is a 3 by 3 times a 3 by 1. That's going to give you a 3 by 1 answer. That's going to be x1, x2, x3. Okay, this is what your x, y, and z. Okay, so let's do it. Minus 1 times minus 1 is 1. Plus 1 is 2. That's going to be 2. Next entry, 1 plus 0 plus 2, that will be a 3. And the third entry, minus 6 minus 2 is minus 8. Minus 6 will be a minus 14. If we check in the book, I got it all wrong. How did I do that? Okay, the 2's right. Is that next one? That's a plus 1. Plus 1 is 2. How in the world did I get that? I must be hungry or something. Okay, let me wipe these out. Okay. All right. Let's do this again. Minus 1 times minus 1 is plus 1, plus 0, plus 2. No, that's a minus 2. How did you let me write it wrong? Okay. That's a minus 2 here. No wonder I got it. Okay. How did I get the first one right? Oh, because it had a 0 there. Okay. So that's a 1 plus 0 minus 2. That's a minus 1. Okay. And then the last one is a minus 6 minus 2. That's minus 8 plus 6, that's a minus 2. 2, negative 1, negative 2. Right. Okay. The next one that we put here is 485. Almost left off my bottom of my 8. That's a 5. It's ugly, but it's a 5. Okay, we do the same thing here. Okay, minus 1 times 4 is minus 4, plus 8 would be a plus 4, so that is going to be, ooh, it's ugly, 4, and minus 4 plus 0 plus 6, that will be a 2. And the last one is a 24 minus 16, I think that's 8, minus 18 would be a minus 10. No. Goodness gracious, what's wrong with my head? Oh, that's a 5, no wonder. Okay, I read it as a 6, sorry. Okay, let me try that again. All right, see this one more time. Minus 4 plus 8 plus 0, that's a 4. Got it. Minus 4 plus 5, that's a 1. I read that as a 6. And this is a minus 6. No. Positive 24. Okay. Positive 24 minus 16, that's a plus 8. Minus 15, that's a negative 7. Yes, okay. Now, that last one is really easy. You put all zeros in here, it doesn't matter what you multiply here, that's 0, 0, 0. And we already knew that was going to be that solution. So the last one is 0, 0, 0. Okay, goodness gracious. Now, that finishes, finally, 2.3. Homework exercises here would include any of the odds 1 through 5. And they're all at calcchat.com. They're also in the back of the book. Okay, back of the book just has answers. Calcchat.com has worked out solutions. Okay, so if you can't get the answer and can't figure out how to get the answer, go to calcchat.com. If that doesn't help, ask me. Okay. Then, any of the odds 7 through 29, you may need some additional help on 27 and 29, but at least do some of those. They're all at CalcChat. 31 to 35, any of those. 37 or 39, either of those. 41 or 43, there's 3 parts each of those. I think we had all those before. Now, 45 or 47, those are like the ones we just did, I think. And then any of the odds, either 49 or 51. Getting to be pretty hefty problems there. And then 53, you should be able to do. It's on calcchat.com. Singular matrix, 55, have they given that definition yet? I don't recall it. Okay. Oh, okay. Sorry. Find X so that, okay. And then 57, you should be able to do that. That's at calcchat.com. 59, also at calcchat.com. These are getting a little harder, so you determine. And then 61 should be at calcchat.com. 63 and 65s are both proof. Well, I'm sorry, wait. Any of the odds 63 through 69 are either proofs or guided proofs, so you can do those if you choose. 71 is a true false. It has 3 parts, so you can do that if you choose. 73 is a writing exercise. You can see what they have at Calc Chat if you want to. That's up to you. 75 is one you should be able to do at Calc Chat. 77 is a proof. 79 should be something you could be able to do at Calc Chat, perhaps. 81 is another writing exercise, and 83. So you can look at those two if you want. We'll begin next time with 2.4. Any question? I know we got sort of rushed at the end and lots of errors at the end. Sorry about that. But any questions? What we did on 2.3. So we'll pick up and go at 2.4 next time. Have a good weekend. And of course, working on linear algebra will guarantee it's a good weekend, right? So I'm going to stop the sharing. I don't like sharing anymore. And unless you have questions, I'm going to end the Zoom session. So if no questions, take care. Have a good weekend. Now I will stop the recording.